All right, so kicking off our bonding unit with our most basic foundations of what you need to know. The good news is that every AP test tends to have a level 1 question somewhere in the multiple choice, just about recognizing types of bonds. So let's make sure that we can do that. People at home, make sure you have your slides. I've also handed out a page of electronegativities that you can access online if you don't have a copy.
I think I'm going to make a song about bonding with blending.
All right, so bonding. Why do elements even decide to bond together? The entire point of making these ionic or these covalent compounds is to add stability. Most of it is dictated by the octet rule when we decide the way that things are going to bond together. Of course, we can expand the octet, as we will revisit later this week, and go beyond 8 valence electrons when we make different shapes like octahedral and trigonal bipyramidal and stuff that's coming soon. So I've got information on the 2 main types of bonds, so let's just read through them for the fun of it. Ionic compounds have electrons being transferred from one species to another. It's the ionic compound where you can actually identify an electron donor and an electron acceptor. You can't do that in covalent. Like we mentioned during the F5, ionics can be defined as a metal bonding with a nonmetal. That's the truest definition. A cation bonding with an anion, or a polyatomic ion bonding with anything is the phrase commonly used. For covalent bonds, there is no donation. Instead, there's a sharing of electrons. If you were in my pre-AP class last year, when I introduced the types of sharing, I used a pizza as an example, realizing that if I bring in an entire pizza, I can give a student exactly half of it. That would be sharing equally, or give them just one slice of it. That would still be sharing, just unequally, because I'm fat.
We're just not giving anybody pizza.
It's true.
Just give me all of you.
The covalent bonds are most commonly defined as a nonmetal bonding with a nonmetal, as we've already mentioned. And they are the ones that can have dipole moments, which is what we're going to be focusing on here in just a couple slides. Now, there is a significant difference of polar versus nonpolar in this class. Do y'all remember last year when we were trying to decide if something was polar or nonpolar, we would do a subtraction thing and there was a range of numbers that you had to see if it fell between, like 1 to 5.5 or 0.55 to 1.5? That does not apply in this class.
Oh, yeah.
It was at recording.
That was really bad. I'm sorry.
Here, you want to come tell them what you read in the restroom?
What did you read?
What'd you read in the restroom?
Anyway.
Sure.
No. I was saying something. AP has simplified this idea. When you're trying to decide if 2 items that would bond would be polar or nonpolar, the only way that you're going to classify it as nonpolar, the absolute equal sharing, is if they're identical atoms. If they have 2 different identities, then it must be polar because they'll have at least slightly different electronegativities, which means one of the atoms will be pulling harder on the electrons than the other, which automatically classifies it as polar, unequal sharing. So, if I just give you 2 elements and I say polar or nonpolar, it's only nonpolar if they're the same element.
And nonpolar just means that they're equal?
Just means the sharing is equal. Nobody is hogging the electrons. Now, the electronegativity difference will still be used, but I'll show you how that is in just a little bit. So, these questions right here go over everything I've talked about so far. So let's pull some cards and see if we can get some right answers.
Do it.
So let's go to cluster 2, seat 4. 2-4. I want you to fill in the first blank. Lithium and fluorine react to form a blank compound. It can be any of the types. Ionic is perfect. All right. which is good. We missed that last class, so I'm glad we didn't miss that this class. All right, that was lithium and fluorine react to form an ionic compound. Oh, you don't have your slides written down?
No, I do.
Oh, you just erased the thing. Sorry, I called you out.
Because
A metal with a non-metal.
I left them blank and I was filling them out, but I didn't know where we were.
All right, let's move on to the second one. I'm going to cluster 4, seat 6. That doesn't exist. Aspen.
what if it means?
Fluorine and iodine form a blank compound, and blank attracts the electrons. What type of compound will F and I, F2 and I2, make?
Covalent.
Now, be more specific. You're right, but what type of covalent? Polar or non-polar?
I don't know.
Well, so are they the same element? Are they the same element? Is fluorine? No. So automatically, if they're different elements, we said we're going to call them like the bear.
Polar.
Polar. All right.
Tell it there.
All right. Polar. All right. And who will attract more of the electrons, the fluorine or the iodine? The definition of attracting electrons is to be electronegative. So who's more electronegative between fluorine and iodine? We just tested over it. Look at your trend.
I didn't do good.
Iodine.
Who's shouting the wrong answer, Isaac?
God damn, is it fluorine? It's fluorine.
All right, here, back here. Guy, this is why third period's destroying y'all. Electronegativity increases right and up. All right? Who is further right and up? Fluorine or iodine? Fluorine is more electronegative. Or, now that I have armed you with this sheet that has the actual electronegativity values, you can...
I forgot my trend.
It's like saying you got a true and false question backwards. That means you got it wrong.
I forgot trends.
Anyway, hey, you will have access to these electronegativities on the AP exam.
What is B? Just kidding.
So make sure that you know to use them. You do not have to memorize them.
Wait, what was the answer again?
The answer was polar covalent, and then fluorine will attract the
Can I come to
electrons.
tutoring and we do the periodic table together?
Now, if you notice, this next section wants you to arrange the atoms based on polarity. What I would like to show you is that this can be done without those values that I gave you for the most part. Because remember, look here. It's going to be nonpolar if they're the same element, right? So really what happens is the closer the elements are to each other, the closer they are to being nonpolar. Now, if they're different, they're polar. But what I'm saying is if I give you two elements that are close together versus two elements that are further away, then the elements that are further away from each other on the table will be more polar. Because the closer they get to being the same element is what makes them non-polar. So if that's true, all right, these are two different ranking systems, so we're just going bottom left. If we look at the bottom left, who do you think is the most polar just based on proximity?
CF.
CF is correct.
Kiriana.
Because look, all three of the species include fluorine. All that's changing is the other guy. And in this case, carbon and fluorine are furthest from each other. Who would be next?
Nitrogen.
Nitrogen and fluorine, because now we've taken a click closer together. And then finally, you will go with your of.
Sagina.
All of this polar is bad.
Well, it's not bad, but the further away they are, the more polar they are in general. Now, you don't have to do this proximity thing. You can do the subtraction thing, all right? If you subtract each of those from each other, the smaller the number is, the more non-polar they are. The larger the number is, the more polar they are, because that means they're further apart on the table.
So if they're not the same element, they're automatically polar.
Automatically polar. And then the question becomes, well, how polar? And that's what this ranking system does. All right, well, Carolyn, let's do this next one together then. All right, we have another set of three over on the right. I want to know which one is most polar. So what I'm saying, Carolyn, look here. If you look at the three duos, which two have elements that are furthest away from each other proximity-wise? I'm asking only Carolyn.
Okay.
CF, NO, or SIF?
Okay.
Yeah, you're absolutely right. All right.
Kiriana.
And now, the backup fact that I said there, Carolyn, is that if you subtract the electronegativities of these two, you'll get a larger number than what you'll get if you subtract the electronegativity of the other two. Because the larger number is telling you they're further away and dictating a higher degree of polarity. What's next on my list?
CF.
CF, and then NO, because of course the NO is only one click away from each other.
Did you get the fun?
It means no. Did you get my joke?
No means no.
Which can be applied to a wide variety of life. Okay. Any questions on this?
Lifestyle.
Nothing. No, I was just talking about the squares. Yeah, no, I don't know. I don't know.
7 clicks.
So let's take a look at dipole moments. This was the only. This is the only thing that confused some students last period. So focus. All right, this is true. So what is a dipole moment? What it is it's a way that we can visually show in a compound who's hogging the electrons.
Yeah.
Oh, I remember these.
We do this based off of electronegativity. So figuring out who's going to hog the electrons, it's easy. It's whoever's more electronegative. You know the trend, you have the numbers, you have a bunch of ways to easily figure out who's more electronegative than who. All right? But what we're going to do is we're going to point an arrow towards the more electronegative, like you'll see that chlorine is more electronegative than hydrogen. All right? And then we do this little plus here, all right, this little tail that actually kind of looks like a plus sign. Because whenever you have your two species here, all right, whichever species is closer to this one is the one that's now partially positive, when whichever species this is pointing to is the one that's becoming partially negative, because of course we're pointing towards the one that's hogging the negative particles.
I based my signature off that.
All right? And this is my symbol for partial.
So, it's a polar covalent. So which one attracts the electrons again?
The more electronegative atom. Further right and up, not counting the noble gases. Now, yes, I made. They're made up letters.
What's the symbol called?
Does anybody know what the symbol's called? I don't know.
Yeah, sigma.
It's not a sigma.
Sigma? Oh wait, are we talking about the S?
Yeah,
Oh, gosh.
I used to know,
Come on,
but
Doc.
I'll look it up. Sorry.
Tell me.
It's supposed to be.
I don't
Now,
know.
the most important thing, and here's where you can get confused in this. AP can ask you about polarity from two different angles. They can ask you if a bond is polar, or they can ask you if a molecule is polar. If they ask you if a bond is polar, that's what we've done so far today. If the two things that are bonding are different, yes, it's polar. Automatic answer. To find out if a molecule is polar, you have to look at all of the dipole moments that exist in there to see if they cancel each other out or not. I'll show you what I mean. All right, we're going to draw some structures. All right, now,
Oh,
I'm not going into the, what, dude?
it's delta. It's lowercase.
Oh, is it a delta?
It's
Okay.
Lowercase delta.
Good.
It's a triangle.
Yeah.
No, yeah, but like lowercase delta is that S thing.
There's uppercase and lowercase in Greek.
Yes. You didn't know that. It's an alphabet.
Hey, Greece. Okay.
Grease.
AP kid.
Percy Jackson.
That's a Bruce.
All right, this is going to click into my lunch because of y'all. Stop.
Sorry.
Thank you. Okay. Hey, when I draw these molecules, I don't want you to get hung up on the why is there a double bond there type stuff. That's Wednesday. We're going to do Vesper again. All right? So just draw what I draw. If you don't remember, you're not helping. So, carbon dioxide. Draw this with me. What I want to do is show all of his dipole moments. In order to show the dipole moments, I need to identify where there's a difference of electronegativity in between atoms. So, looking between these two, all right? Is there going to be a polar bond between them? Yes, because they're different. Which direction will the arrow point? Towards who?
Towards
Towards oxygen, because oxygen is the more electronegative of the two. That would make carbon be my partial positive and oxygen be my partial negative. Are you with me so far?
Can I just say that this
Why
is
is it
way
the
easier than how nothing explained it last year? Sure.
Josh, you dare talk about my doubles like
This bond looks like it's identical, right? So we will therefore show it this way. All right? Oxygen is more electronegative than carbon. Therefore, there's to be my partial negative. This will be my partial positive.
that. But it is a better job.
And here's where the AP will trick you. If they ask, does this contain polar bonds? What's the answer?
Yes.
Yes. There's two polar bonds there. If it asks, is the molecule polar? The answer is no. Because these two dipole moments are perfectly canceling each other out. Not only are they pulling opposite like tug of war, they're pulling equally opposite. Do you see?
Yeah.
This is a non-polar molecule that has polar bonds.
You get it. You get it.
So really, when I draw it, I wouldn't even show the arrows since they're not there. You could do it in your work. If you're doing an FRQ and it was obvious that you were just checking the dipole moments, you would just want to then redraw it without the arrows because it's like it's not even happening. All right? Like if me and Jacob were to arm wrestle, aside from me obviously breaking his arm, but if me and Jacob were to arm wrestle and we were equal, you wouldn't want to say, our hands wouldn't be moving if we were equal. It'd be totally still. So there would be no point in even saying that whether we're both trying or both not trying. All right? You don't show the dipole moments if they cancel each other out.
So do you still show like the X's and stuff?
You don't show any of it.
You only show S.
Yeah, pay for my hospital.
That's it. That is a non-polar molecule. All right? Now, there's the polar bonds are still technically there, but if it's a non-polar molecule, you won't show any dipole moments. They don't exist. All right, let's do the next one. All right, hydrogen iodide. Here's what he looks like. Do you see a polar bond anywhere? Look, this not, I don't want y'all to I don't want you to overcomplicate that question. Are the two atoms different from each other?
Yeah.
Then you've got a polar bond. All right. Which direction should I point my dipole moment? Towards the I. Because iodine is more electronegative than hydrogen. That's going to make hydrogen have a partial positive charge and iodine have a partial negative charge. So we've identified bond polarity. Now, just like the slide says, I want to identify molecular polarity. Is it a polar molecule?
Yes.
Yes.
Yes. Look, it's pulling that way and nothing's stopping it. It's pulling that way and nothing is offsetting it. Nothing's canceling it out. So this is a polar bond in a polar molecule. The last one was a polar bond in a nonpolar molecule. Do you remember nitrogen?
No.
There's nitrogen. Do you see a polar bond anywhere? No, right away. They're identical. It's two nitrogens. We don't have to check anything else. All right? This is a non-polar molecule. All diatomics are non-polar molecules.
So if it's not
Ringelhoff.
polar, it's like not polar everything.
Yes, yeah, right away. Non-polar everything. Because there's not even a bond to try to draw a dipole moment, so there couldn't possibly be an overall dipole moment if I'm not going to draw any arrows, period. Yes, and that's another diatomic example you just gave, but yeah.
Wait, was she dipole members? You're not saying it's dipole interaction?
No. That's an intramolecular force. That's next unit.
That's-
Yeah. Those dipole-dipole interactions are where different molecules are attracted to each other. We're not doing that. Those are already established compounds. All right, well, let's take a look at the one that'll make you angry. All right, CCl2F2. It looks fun. Let's check them out. Draw with me.
With the sunshine.
No.
Yeah, you're like making a triple sun.
It's a sun snowflake. I like that other day.
Oh, snowflake here, snowflake.
It is. It's a chemistry snowflake. It's a chemical snowflake. That's what a Vesper model is.
Cute.
Not 100%.
Everybody okay with what I've done so far, aside from we didn't draw the Vesper from scratch? All right,
No.
do you see how it represents the molecule?
Yes.
What are the extra ones on the F's and CL?
Those are lone pairs. I didn't feel like drawing a million dots.
Okay, cool.
They're unbonded, so they really should be dots, but that's acceptable. All right, let's go through our questions. Do you see any polar bonds?
Yes.
Yes.
How many?
4.
There's 4. Yeah, look. This is going to point towards chlorine. This is going to point towards chlorine. This is going to point towards fluorine. This is going to point towards fluorine. Do you agree?
Yes.
I pointed the arrows towards the more electronegative atoms of the pairs.
That looks like the Christian symbol for Jesus.
Now I have to delete the video.
I love that shirt.
Why? It's like a
Because Satan hates it when you say that. I'm just kidding.
You look so serious.
No,
I remember the Super Saiyan joke.
Super Satan joke. That was with 4 6s, right?
Yeah.
That's good. I like that joke.
I remember that.
We did Naho last week.
You were like,
It's pretty good.
nosebleed.
Now for the other question: Is the molecule polar? What do you think? Is the molecule polar?
Yes.
No. Yes.
You're arguing with each other.
It's polar because there's none.
You're expecting us to say no, so it's obviously yes.
Oh, Mira, look, she's right. They all cancel each other out.
No, but the COs and F's are. It's not like an F.
Yeah, but they.
Yeah, but
Yeah, that's true. I'm saying
They're
it's polar.
two.
I'm gonna go
It's
over.
non-polar.
This
but
is
they're
a
different.
polar molecule.
Said it. I said it.
There is a net dipole moment, and that net dipole moment is here.
Well, that's a different.
Why did I put it there? Why would it make sense that that is the correct place to draw the net dipole moment?
The F's are stronger.
The F's are stronger than the CL's, and so what I did was I averaged their direction.
Wait. What if you put the other F up top instead of using CL? So like the Christian.
Show me how to do that.
Oh, damn it.
But
Wait, do what? What are you saying?
Yeah, go.
Go ahead. Yeah, go
For
ahead.
those of you at home, the question was, but what if there was an F down here and an F up here, and that chlorine was there? It's impossible. That's not how the 3D world works. Therefore, it doesn't matter. I'm not insulting you.
Your shit is so bad.
That's not what I mean. It's the stupidest question
That's
all day.
not
No,
how
I'm just kidding.
3D world works, dummy. We don't live in 2D.
You know that's not what I was saying.
No, that's exactly what he said.
The reason I have this is to anticipate that question. So,
For people like you.
anyway, if the F's were drawn this way, I would need that to be drawn into the whiteboard. So it's just I wouldn't be able to draw it. So if you were having to draw the net dipole moment on an FRQ, you couldn't draw it like that. So you'd have to draw it. You'd have to have the F's be next to each other, even though they are all identical. It doesn't
We were
matter.
drawing like the little lines to show like which way it was like.
That's IMFs again. That's next unit. It's intermolecular forces.
So, like, how do you even know that's exactly how it's drawn?
I'm good.
Because, like, if you told me to just draw that right now, I probably would have.
Yeah, I would have no idea.
Yeah, I probably would.
It's, you know what? If you're not having to show the net dipole moment like this, then it wouldn't matter. You could put the F there and the CL there because again, it's just floating through space. All it's doing is floating through space, and it's going to orient itself like that, and then it's going to orient itself like that. None of them are wrong, but for you to be able to draw on a flat surface that arrow, the F's cannot be separate from each other because you'd have to draw it into the wall.
I agree.
I'm sorry?
How do you know it's drawn that way though? Like if you're just giving out on like
I'm going to show you that on Wednesday.
Wait, why?
On Wednesday, we're going to start Vesper all over on Wednesday on how to count bonds and do all that.
Enrichment.
Wait,
All right.
You're telling me we have 4 lectures
No, tomorrow's an extra credit opportunity.
Why did fluorine win again?
Because fluorine's more electronegative than chlorine.
Because it's
The-
higher?
Because he's further right and up, or he has the higher number. Both of them are the same idea.
The more positive, like the higher.
Okay, let's keep going. I'm going to run out of time.
So if they were all CO, then it would cancel out?
Then, okay, good question. What if they were all chlorines? Then it would be polar bonds, non-polar molecules, because they would perfectly cancel each other out. Way better than that other question.
Yeah. Diego just isn't gonna breathe today.
Diego, if you didn't ask me that question, I was going to have to ask it to y'all myself. So I appreciate you. Okay, lattice energy. So I want you to realize that we have been focusing on the last 10, maybe 15 because of y'all minutes on just covalent. Remember, the polar, the non-polar, all that stuff, dipole moments, covalent only. Don't mess that up. If we're going to analyze ionic a little bit deeper, then that's lattice energy. Lattice energy is the amount of energy released when you form a crystal. Remember, ionics are described as being crystals, while covalents are described as being molecular. So that's another general difference to always have in your bag of vocab for FRQs. Now, realize that forming a bond always gives off energy, all right? Because to break a bond, you'd have to input energy, all right? But what's nice about describing lattice energy connected to how ionic something is that the equation for lattice energy is the same as Coulomb's law. Do you remember Coulomb's law from last unit? Coulomb's
Coulomb
law.
law states that.
Coulomb's law was the one
Isn't
that put
right?
Q1 and Q2 over radius, which stated
Oh,
that
yeah, he talked about some radius.
it stated that if the charge was greater, then the attraction was greater. But if the radius was larger, the attraction was much smaller because it's divided, right? If this is a big number, it would divide it and make it go down. It was when we had to deal with if the electrons were further away from that nucleus. As the radius got larger, the attraction between them went down. The same thing happens here. The lattice energy equation, when you look at how ionic something is, uses this exact same setup. This is really powerful for you to know because when you're asked a why question on the AP exam, you're going to have to either say lattice energy, which is that, or you can say Coulomb's law. Why? Because it's also that. They're identical to each
Will
other.
we actually just say Coulomb's law?
You'll reference it in your answer.
Okay.
Because if you don't, they won't give you the point. That's my point. If they ask you why lattice energy and ionic character works the way it does, then you have to use one of those two phrases.
College board hates us.
So, if you look at this compared to what's on the bottom there, it says more charge equals more lattice energy. Yeah, well, that means that if these values are larger, that's going to overall equal a larger quotient, all right? But more radius will be less energy. If that denominator is bigger, then you're dividing by a larger number, which will make the quotient be smaller. So what does all this mean? Let's take a look at a couple questions to end the lecture.
Victoria, why does it make this sound?
Before you write anything, look here. I want to explain something. When it's asking you how ionic something is, which is what this is, ionic character, there's two different angles that they might want you to explain from. There's the what. This is a what question. It just wants you to rank them. Which one is the most ionic versus the most not ionic, since they're looking from an ionic point of view. All right? If they're asking you to rank it, the difference of electronegativities is what you want to go back to. Anytime they give you these pairs and you're trying to figure out whether it's falling towards polar, non-polar, polar, or ionic, just find the difference in electronegativities. Real quick, I want you to do that. Rank these from most covalent to most ionic.
Can we take out lithium hydrogen?
Yeah, take out lithium hydrogen. There's a good reason for it. I'll explain it when I'm not on a time crunch on a video.
Most to least and least to greatest.
The most covalent to the most ionic.
Wait, how does the covalent
everything. So it's just a flow because it goes non-polar, and then it goes to polar, and then it goes to ionic. All right, that's our basic flow of character. So what I want to know, we remember that down here, this is where the numbers, the difference are closer together, and this is where the difference is further apart. So you can rank it based on that scale. So find the electronegativities of everything, of each pair, and subtract. And find out, well, if they're closer together, then it's more covalent.
So
If they're further apart, it's more ionic.
So then when I get the difference, would the
I
smallest
get up to
difference-
ionic.
The
Alright, let's
smallest
do that.
difference would be more. Oh, that
The smallest,
because it's
smaller
closer.
number.
Oh,
The
yeah.
numbers are closer together.
Okay,
Yes.
okay.
This is a smaller number. This is a
Oh, no.
small number. This is a big number.
Wait, smaller is less ionic.
Yes.
So then the smallest one is most covalent.
Yep.
All right. I only have 5 minutes, and there's another question after this. Let's go over to cluster 5, seat 1. 5-1. Who did you say was the most covalent?
No, HF.
HF. Do y'all agree or disagree?
I agree.
Disagree.
No, I disagree too. I say HCl.
Yeah, I said H.
So the HCl only has a difference of what? 0.9?
0.9, yes.
All right.
And it's HCl.
And then the HF has a difference of what? 1.9.
Yes. And
All right.
NaCl is 2.1.
Hey, how could you have known that NaCl was the most ionic without even doing
It's
this?
an ion already.
It's the only one that contains a metal. Now, this is an easier one because I knew I'd run out of time in lecture, but like your Schoology assignment, they have a question like this that has, I think, 8 that you have to rank. But it's easy. Find all of these numbers and then just make sure that you put it in the correct order.
Just do a lot of work.
Right, okay, so then
Wait,
smallest
what's the order?
is-
What's the order?
And then it's H and then NaCl.
What was the first two? Oh,
This is the order. This is from most covalent to most ionic.
I see.
To the last slide, please.
Well,
This is great.
Here's an actual AP question. If you notice what it's doing, it is giving you different lattice energies of salts of potassium. So there's potassium fluoride, potassium chloride, right? Potassium with different halogens, it looks like. And it wants you to explain those numbers based on both charge and radius, all right? Well, that's Coulomb's law. That's lattice energy. Charge and radius, that's exactly what that looks at. So, yes, this wants you to answer the question, but if you don't involve one of those phrases, you're wrong. So take a look. It wants you to look at it in terms of size and charge, it says. What's true about the charges of all 4 salts? They're all the same. Potassium is +1, and all 4 of those halogens are -1. So I would want to mention in my answer, there is no difference in charge between any of those 4 compounds. Therefore, what must be the reason that the potassium iodide has such a lower lattice energy than the potassium fluoride? The radius. Because what happens as you go down that group? It gets larger. And what happens if the radius gets larger?
less attraction.
Less attraction, and in this case, there's going to be less
Coulomb.
lattice energy. And if somewhere in there you say the lattice energy equation, or because of Coulomb's law, that's what finalizes it for you.
Iriana.
If I can't remember, it should be like blah 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 because of
Have we finished the lecture?
oh, for the bets.
There is a hybridization lecture online that you must watch. I'm not